Assalamu alaikum. We will start lecture 29, and in lecture 29 we will start chapter number 6, that is shearing stress in beam and thin wall member. So the topics we will cover: 6.1 horizontal shearing stress in a beam, which we have three component. We will discuss one by one these component. So this lecture will be horizontal shearing stress in a beam. First, we will see shear stress on a horizontal face of the beam element. Then we will find and determine the shearing stress in a beam and the shearing stress tau xy. We will see why we are written tau xy over here in common types of beams. Next week, we will discuss about longitudinal shear on beam element of arbitrary shape and the shearing stress in thin wall member. Okay, let's start with this topic 6.1, shearing stress in a beam. Okay, first, how we know that there is a shearing stress in a beam? For example, we have this simply supported beam made up of multiple planks. Uh, multiple planks, and these planks are not bounded together. Okay. Now, when we applied load, what will happen? That this plank will try to slide with respect to each other. Means there must be a force on the interface that is causing slippage, and that force is acting parallel to that area, not perpendicular to that area. So that's why there must be some shear force acting on that. Now, why we cannot see in common examples, because usually they are bonded together, and still they are bonded together, but there must be a force acting between those planks. Okay? Or if you consider cantilever beam with the end support, so if you apply load at the free end, so made up of this multiple planks, so the plank will have uh, will slip with respect to each other, means there must be a some shear force acting on parallel to the surface of the plank, and that's causing the shear between them. Now, if we have a rigid plate and we applied bending moment, so that will not the case. In case of pure bending, this will not happen. This will be only we will considering if we have a multiple planks. Okay. Now, over here, if you look at again this cantilever beam with a shear force acting over here, when we apply shear force, now the shearing force will cause distortion. Okay, so this section of the beam will distort it, and means there must be some shear stress acting on this surface, and we will find with this horizontal component. So that's why the topic is horizontal shear. So there must be a shear force acting on this face like this. Now if I take a small element out of that, so there must be a longitudinal shear stress. So we will first find what is a longitudinal shear, and then with that we can find what is this transverse shear. So we will take indirect approach as compared to previous approach that we consider deformation. No, in this case we will not consider deformation, because if you look at the deformation is quite complex. That's why we have to take indirect approach for this uh, uh, shearing stress. Now, if you remember from chapter 4, uh, when we have a pure bending, so we discuss what will the forces acting on the element. But now, in this case, we have a transverse force as well. So previously we have only bending moment, but in this case we have internal shear force or transverse force as well as bending moment, internal bending moment acting on the section. So the transverse load being applied result in normal and shearing stress in a transverse section. For example, uh, if we consider a cantilever beam, if I have a cantilever beam, there is a point load acting at the free end. So if I take any section, so there will be a bending moment as well as a shear force. Now, or if I take a simply supported beam, uh, and with the concentrated load or maybe distributed load, if I take any section, so there will be a bending moment as well as a shear force, internal shear force. So transverse load applied to a beam, so uh, that will cause result in normal and shearing stress in the transverse section, because we have a shear force that will cause shearing stress and we have bending moment. Now, distribution of normal and shearing stress, so Fx, that will be 0, because if you remember that first moment of, for the whole cross section, first moment of area must be equal to 0. So this term will be 0. And we have Fy. Now in this case, when we have transverse load, we have tau xy shear stress. Now why tau xy? Because the section is perpendicular to the x-axis and the force is in y direction. So this upward component is your tau xy, and the sum of these forces must be equal to V. And tau xz will be 0 because there is no force acting along z axis. Again, that is depending on the coordinate system. According to this coordinate system, we have x, y, and z. So the shear force is acting along y axis, and the moment is about z axis. So that's why Fz tau xz is equal to 0. Now, moment about x is 0, moment about y is 0, whereas moment about z will not be equal to 0. So it's written wrong over here. So that should be equal to mz. And this will change into flexure formula mz, and that will be equal to, sorry, not that will equal to m, not equal to 0. Okay. And this, we know that cross moment of area was equal to 0, and there is no moment about z-axis, x-axis, so that's why these terms will be 0. Okay, so when shearing stress are exerted on the vertical face of element, so they must be exerted on the horizontal face as well. If you remember from chapter 2, so when we have shear stress, if we consider the 2D element, if you remember that, if we take 2D element, so we have tau xy in this direction, so they must be tau yx, and similarly on these faces as well. And we know that tau xy is equal to tau yx. So now if I take a small element over here, if I take a small element, and that element, if I want to draw shear stress, so there will be a shear stress on this face due to V, this V, and there must be a shear stress on the horizontal face of the element. And we have, obviously, we have shear stress on the back face and the down face, and this is stress normal to that area, and that will be a sigma x, normal stress. So when shearing stress are exerted on a vertical face of an element, that equal stress must be exerted on the horizontal face. So in this, how we will find? So we will find this horizontal component, and then it's related to, and it's equal to this vertical component, and we will find the value of that vertical component. Okay, so longitudinal shear must exist in any member subjected to transverse loading, but that is not case of the pure bending. Okay, but if you have transverse loading, then you have a shearing stress, and it will have a longitudinal shearing stress and as well as transverse shearing stress. Now let's consider now how to find that stress, that component. So first, let's consider a beam like over here, simply supported beam, and this simply supported beam A and B, we have a point load P1, P2, and we have a distributed load. So if I take any section, so there must be a transverse force as well as transverse shear as well as bending stress. The cross section, we have a prismatic beam, and y-axis is the axis of symmetry in this case, and x-axis along the axis of the beam. So if you take any section, so the cross-sectional view is given over here. So now z-axis, we have y-axis. So now let's take a section over here and take a small element or section from here. We are taking a section from here, and this is the section we are looking at. Now this is, let's take the small element C, D, C prime and D prime. So if I look at this section of that, so this is the element. So C or C prime. Okay, so we are interested on this shaded area, means what is the horizontal shear force acting on this surface. We are interested to find what is the horizontal shear force acting on this surface. Okay, now if I draw force diagram or free body diagram for this segment, okay, so let me change the color. So if I draw a free body diagram, for my interest is on this segment only. So free body diagram will be like this. So we have a distributed load W. So at C we have a shear force following the sign convention. If you remember, if you're taking section from right to left, so shear force will be upward taking as a positive. If from taking from left to right, so this downward will be positive. We take shear force downward. So, and this is a normal stress distribution on this area. Okay, sigma d, the normal stress, bending stress multiplied by dA, that will give me the force, and sigma c dA, that will give me the force acting on this surface, C prime surface, and D prime surface we have sigma d dA. Now these uh, forces will not equal, sigma c dA and sigma d dA, because the bending moment is changing from C to D, and also shear force is also changing from C to D. Okay, now, and we have a distributed load W. So there must be, so since these two forces are not equal, sigma c dA and sigma d dA, so there must be a force acting along this direction that will balance these forces, because sum of forces must be equal to 0. And how we know that? If you remember previous slide, that the slippage of planks, that's movement of planks with respect to each other, that gave an idea that there must be a force. Now this delta H is a shear force acting at this bottom area, right? At bottom area. Now let's take the sum of forces in x direction must be equal to 0. So if I want to write sum of forces in x direction is equal to 0, so delta H taking positive plus integral sigma d minus, sorry, this must be sigma c minus sigma d. Okay, so this is again, this must be sigma c minus sigma d dA. So and integrating for this area. So we are interested what is the shape delta H over this area. So this A is this area. Okay, now simply rearranging it. So taking delta H over here, so multiply with the negative, so delta H. Now sigma C, I can write sigma C will be what? Moment at C, that Y divided by I, and sigma D is moment at location D, Y divided by I. So putting these in this equation, so MD and MC, so that will become MD minus MC divided by I integral over that area Y dA. Okay. Now, what is this expression? This is first moment of area. If you remember, this is first moment of area. And for the whole cross section, it will be 0, but for this section, we have some value. So this Q integral A dy is the first moment of area. So that is first moment of area. For the whole cross section, it must be equal to 0, but we are interested only this section, so we are taking only for that section. Now, if you remember from previous chapter, MC minus MD, and if you multiply and divide both by delta X, so this I can write dm divided by dx into delta X, and that will be equal to V times delta X. So if you remember that from previous lecture, so dm by dx is equal to V. So what we are doing, we are multiplying both sides with the delta X, and that will be equal to difference of moment on both ends. So delta M MD minus MC is equal to V times delta X, that is area under the shear force curve, or we can write this as well, this form as well. Now if we replace MD minus MC, so we can relate this shear force with the transverse load, with the internal shear force. So if simply replacing this expression with V delta X, so delta H will be equal to V shear force Q first moment of area divided by I into delta X. And what is delta X? Delta X basically this distance, only this element distance. So this is we are taking as a delta X. So simply A, if we take delta H by delta X is equal to VQ over I. So this is known as shear flow. So this expression is known as shear flow. Okay. Now, in case of pure bending, this V will be 0, so shear flow is 0. But if we have a transverse load, then this shear force cannot be zero. So but the shear flow, or this value of shear flow, will change from location to location depending on the loading on the beam. Now, this shear flow is very important. For example, let's see again. So we calculated shear flow Q for this shaded region. We calculated this value of Q, that is shear flow for top this region. Now on this surface, if I take a bottom region, so I can take Q for the bottom region. So in that case, so shear flow, let me write Q prime. So in both cases, the shear flow must be equal. It will be equal, but opposite in direction, because the total, if I add this Q plus Q prime, it must be equal to 0, because first moment of area for this whole cross section must be equal to 0. So Q plus Q prime will be equal to 0, first moment with respect to, so this with respect to neutral axis is 0. So this Z axis, this is my neutral axis. So if I'm taking the first moment of area with respect to neutral axis, it must be equal to 0. And we discussed this in chapter number 4. So this Q over here is first moment of area with respect to this neutral axis, but above this, on this surface. And now this shear flow will change with Q, this first moment of area. Or we can say delta H will also change with respect to, on the given cross section, with respect to first moment of area. And for the whole cross section, it will be 0. And if you look at the top surface, so top surface, the area is 0. So the shear flow Q, the first moment of area will be 0, and the shear flow will also equal to 0. And at the bottom, again, if we're considering the whole cross section, so Q plus Q prime will be equal to 0. So at the bottom, this shear flow will also equal to 0. And it will change from the depth of the beam. So it will change with respect to depth of the beam, this shear flow. Okay, why the shear flow is important? So let's see an example, a concept application. So we have a plank beam is made up of 3 planks as shown over here. 1, 2, 3. These are 3 planks, and they are bounded together or nailed together. So there is a nail over here and over here. So if you look at the beam, so we have a beam with the nails, 1, 2, 3, 4, multiple nails. It's a whole long beam, and we have a nails at a fixed position. Knowing that the spacing between the nails is 25 millimeter, means if we saying that the distance between one nail to another nail is 25 millimeter. So the spacing between the two nails is 25 millimeter. And the vertical shear on the beam is 500 Newton. So if I take any section on the beam, so it's given that the shear force is acting is 500 Newton. So we have a constant shear force acting on it. So we have to find what is the shear force in each nail. How we will find? Means if we remove this top plank, and if I draw it, so by removing the top plank, so what is the shear force acting on that surface? And obviously that shear force will be acting on the nail as well, because this plank will try to, the top plank and this middle plank, it will try to slide on this surface, and that will cause shear force on the nail, and we have to find what is the shear force on that nail. So for that we have to calculate what will be the shear flow. First we will calculate shear flow, and using the space between the nails we will find what will be the shear force acting on that. So if we multiply the shear flow with the nail spacing, so let me write space, that is 25 millimeter. So we will get what will be the force acting on each nail, force on nail. Okay. So how we'll find, we will determine horizontal shear force per unit length or shear flow on the lower surface of the upper plank. So we will find on the lower surface of the upper plank, and then calculate the corresponding shear force in the nail by using this relationship. Okay, now let's calculate. For that, we know that the formula for shear flow, uh, that is Q is equal to, that shear flow is equal to VQ over I. Q is the first moment of area, so we have to find the first moment of area. So we are interested shear flow at the lower surface of the upper plank. So we have to calculate first moment of area for this, for the upper plank on this. So we can find what is the shear flow on this interface of upper plank and the middle plank. Okay. Now for value of Q, that is first moment of area, that is A area multiplied by Y bar. Y bar is the distance from the neutral axis, and neutral axis will coincide with the centroid of the cross section, this whole cross section, to the centroid of this shaded area. So that is 0.060. Okay. Now putting the value 120 10 to power minus 6 meter cube. So 0.02 by 0.1 is the area, and 0.06 meter is this distance. Now we will calculate I for the whole cross section, and that will be I for the web 1 by 12 ph cube plus 2 times I for upper plank and the lower plank. So 2 times 1 by 12 ph cube plus area into d square, that is parallel axis theorem. Okay. Now we know what is the shear force, 500 Newton, that is supplied constant. Q we calculated, so that is 120 10 to power minus 6 meter cube, and we calculate I. So putting the values, so we have shear flow of 3704 Newton per meter. Now we know the spacing between the nails, so that is 25 millimeters. So calculate the corresponding shearing force in each nail for a nail spacing of 25 millimeters. So force on each nail will be 0.025 meter multiplied by Q, and put, so on each force the shear force of 92.6 Newton is supplied. So now if you designing something, so you have to consider joining two planks, so you have to consider what is the force acting on each nail as well. So this force will change with, and you will decide the nailing space or joining space according to that. Okay. Now this shear flow, now we extend this shear flow to find what will be the shear stress. Now coming back to that area, that same beam, okay, so same beam with the delta x is the distance, this is along the length of the beam, and this lower area, so let's take this lower area. So we calculated what is the shear force delta H on this, and that delta H was, if you remember previous slide, that simply the delta H was equal to V Q divided by I into delta X, that we calculated previously, and that delta H by delta X was equal to Q, that is shear flow, and that is VQ over I. Okay. Now let's take this bottom element, and we calculated shear flow, shear force on the horizontal face, this face, and we are interested what is the shear force or shear stress on that. Okay. Now if I divide this delta H with this area, this smaller area, delta A, so that will give me the shear stress. So this average shear stress, tau average, is what, delta H by delta A. Or delta H I can replace with the Q. So delta H is also equal to Q times delta X. So I put the value divided by delta A. And Q, I know that that is equal to VQ over I delta X. Now this delta A is what? This dimension, that is equal to T, and this dimension, that is equal to delta X, or also shown over here. So that area, if I put the value of area, T into delta X, this delta X will cancel out, so that shear stress will be equal to V shear force Q, first moment of area for this region, this shaded region, divided by I, second moment of area, moment of inertia for the whole cross section, divided by T, and T is this dimension. So if I am interested what is the shear stress on this region, so that T will change and T will be according this one. So VQ or IT, that will give me the shear stress on the cross section. How? Because this is shear stress is horizontal one, so there must be a shear stress acting on this face as well. So if you remember from the previous slide, so if I take a small element, so shear stress, so there's a shear stress acting on this surface, so there must be a complementary shear stress acting on the this this vertical surface as well. And this is the element we are talking about, small element we are taking. Okay. Now on the upper and lower surface of the beam, tau yx will be 0, so it follows that tau xy will also equal to 0. So this component is tau yx, so it must be equal to tau xy. In the top and bottom surface of the beam, this component will be 0. Why? Because over there the shear flow is 0. Okay, or in other words, the first moment of area will also 0. So since first moment of area at the top surface, if you are only taking top surface, so there is no area. If we're talking about lower surface, and if I'm integrating that first moment of area from top to bottom, so it will become a whole cross section. For whole cross section, the Q will be equal to 0. That's why the shear stress will be 0 at the top and bottom surface of the beam. But now, what will be the shear stress distribution? Okay. Now let's take this rectangular cross section. So we have a rectangular cross section beam, and we have this dimension, this whole dimension. The depth of the beam is total h, or we can write this dimension 2c is equal to h, and the width of the beam is b. This is giving the cross. This is showing me the cross section of the beam. Okay. Now we know that tau xy from the previous slide, that tau xy was equal to vq over I t. Now t over here is equal to b, so we simply replace t with b. So over here t is equal to b. Okay, now let's consider the shaded region. Now let's consider the shaded region. So first, I for the whole cross section for this beam is what? 1 by 12 bhq. So I for the rectangular cross section, 1 by 12 bh cube, and we know that h is equal to 1 by 6, h is equal to 2c, so we can write 1 by 12 b 2c cube. So we can put the value of I over here, 1 by 12 bc 2c cube, and value of q will be what? Value of q, if I take this region, shaded region, so y prime area, this area will be some dimension, so that will be c minus y, so this region, right? And the area will be equal to multiply by b, so this will be giving this area, and this distance, so I can write c minus y divided by 2. So if I get this dimension, so this dimension c minus and plus y, so y plus half of this, so it will give me this value. So if I put it and simplify it, so that will become 3b divided by 2a. Now area is p multiplied by h for the whole cross section, b multiplied by h, or b multiplied by 2c, and multiply by 1 minus y square by c square. So by putting these value, you can simplify it and you will get the value of the shear stress tau xy is equal to 3v by 2a 1 minus y square by c square. Now, where we have maximum shear stress. Now if you look this expression, so maximum shear stress when y is equal to 0. So if you put y is equal to 0, so this term will become 0. So when we put y is equal to 0, so let me change the color. So when I put y is equal to 0, so this term will become 0. And what does it mean? It means that at neutral axis, or at the axis passing through the centroid of the section, that is neutral axis, my neutral axis, at that we have maximum shear stress, that is 3v divided by 2a, and that is for the rectangular cross section. Now if you look at this expression again, if I'm looking this expression, so shear stress distribution is parabolic. It will be, and at y is equal to c plus minus c, that is top and bottom surface. So if we put value of c, so 1 minus 1, it will become 0, so shear stress will become 0. So shear stress distribution will be parabolic. It will be maximum at neutral axis, and it will be 0 at top and bottom surface. So usually the shear stress distribution is parabolic, and at the top and bottom surface it will always be 0. Now, if we consider flanges, flange type beam, S and W beam. Now, if you look at, let's suppose this is a W beam. Now, in that case, the shear stress distribution is for this top flange region. The shear stress distribution will be very small, but for the web region, it will increase and it will be maximum at the centroid of the section or the neutral axis of the section. So why? Because the value of T is very large for the flange. So value of T is very large over here. So that's why the shear stress distribution is very small. Because if you look at the formula, so T is equal to VQ over IT. Now at the web, T is very small. So this value is very small. And again, Q is also increasing. That's why it is very large at the web. And the generalized formula for S-type and W-type beam we can write as tau max is equal to V divided by area of the web. So area of the web means area of this region. E, F, E prime and F prime region. So this area of the web. So this will give us the maximum shear stress for the S and W type beams. And if you want to find at any location, so we have to calculate Q for that and what will be the T of the value T, so we can find what is the average shear stress at any location. So but the shear stress distribution is not linear or uniform in case of transverse load. So let's see a sample problem. So this sample problem is a timber beam. We have a simply supported timber beam uh, that is supporting three concentrated load. Knowing that for the grade of timber used, sigma allowable is 1800 psi and tau allowable is 120 psi. Determine the minimum required depth D of the beam. Now in this case we have to find what will be the value of D for the maximum bending moment and then value of D for the maximum shearing force. And we will select whatever the largest is, both of them. But for this loading, what we will do, we will develop shear force and bending moment diagram to find maximus of shear force and bending moment. And we will determine the beam depth based on the allowable stresses. Determine the beam depth based on allowable shearing stress. First, we will find with the normal stress and shearing stress, and we will select which is the larger between both of them. Okay. Now, shear force, first, in order to draw shear force, we have to calculate the support reaction at A and B, and then we can calculate we will draw shear force and bending moment diagram by taking section at different location. And we did this on previous chapter. So quickly, if I take this section A to C, if I want to write, so this I'm doing this quickly. So A to C. So I have a 3 kilo-pound acting over here. So shear force acting I will take positive, and bending moment M counterclockwise I will take positive, and this distance is x. Again, this is for section AC. So simply V minus 3 is equal to 0. So V will be 3 kilo-pound inch. And M minus 3x is equal to 0. So M will be equal to 3 times x. So x is equal to 2 feet. So from it will be 0 at A and 6 kilo-pound feet at C. And similarly, if I take section just before D, so we'll let me do over here again for section Now this is for the section CD, but we have to draw from here 3 kilopounds. So we have 2.5 over here. So let me change the color of my pen so that will become easy to understand or to distinguish. So 2.5 kilopound. So shear force V acting downward will take positive and moment M in this case will positive. So shear force I can write V plus 2.5 minus 3 is equal to 0, and this will leave me V is equal to 0.5 kilopound. Now if you look at the shear force from C to D, it will be 0.5 kilopound. And for the moment, so I can write, M plus 2.5 multiplied by X minus 2 feet. So for this one, so this distance is 2 feet, and this whole distance, this distance is 2 feet, and I'm taking this distance as X. So this distance will become X minus 2 minus 3 into X is equal to 0, and M will be equal to 3x minus 2.5 x minus 2. Now if I put x is equal to 5, so this will become 15 minus 2.5 times 3, so that will become how much? 7.5. So that will become 7.5 kilopounds fit. So, and the shear force will be, bending moment will increase linearly, and 7.5 kilopound fit will be at D, and you can calculate further. Now the maximum shear force is 3 kilopounds on that section, and it will be located between AC and EB, and the maximum bending moment is 75 kilopound fit or 90 kilopound inch multiplied by 20, 7.5 multiplied by 12, converting into inches. The maximum value is T 7.5 kilopound. Now, if we calculate sigma allowable, 1 by 12, 1 by 6 BD square, that is section modulus for the rectangular cross section, or you can calculate sigma allowable is equal to M C max by I. You can calculate like this as well. So sigma allowable was 1800 psi, 90 pound fit, 90 kilopound fit was my bending moment divided by section modulus in terms of D, because D is unknown, so only this dimension is known. So we put the values of D become 9.26 inch. So with base on normal stress, the value of D is 9.62. Now for the shear stress, it's a rectangular cross section. So tau max or rectangular cross section will be 3 by 2 P by area. So we put the value. So by putting the value 120 psi, 3 by 2 shear force, we calculated the maximum was 300 pound divided by 3.5 into D, that is area. So D become 10.7 inch. Now we have to calculate the maximum dimension. So we will calculate required depth will be 10.71 inch. Okay, but if it took 9.26, it will fail in shear. So we have to select the maximum. Now The important parameter point is for the rectangular cross section, the value of shear stress or shear stress distribution will depend on the rectangular cross section, means the ratio of B by H. Now, for ratio of B by H, now if I take, let's suppose, C prime, this section, this is my neutral axis where we have maximum shear stress, and this B by H ratio, the shear stress distribution will be almost uniform. It will be maximum neutral axis, but with the ratio of B by H changes, the shear stress distribution on the neutral axis will also change. So if it's 0.25, means the width of the beam is smaller, very smaller, or ratio is 0.25 with respect to height of the beam or depth of the beam. So in that case, the maximum shear stress is equal to average shear stress. At 0.5, it will be ratio, it will be same. At 1, we can consider almost equal, but when the width of the beam increases, this ratio is changing. Means that this relationship of tau max 3V by 2A is only valid where B by H ratio, or where the depth of the beam is larger than the width of the beam, or almost equal to, or equal to B. But if the width of the beam increases with the depth of the beam, so we cannot apply this formula because it will give us the wrong value of tau max. So if for the lower value, so it is the tau max we calculated from this formula will be fine, but it has a limitation as the width increases, so we cannot apply this formula. So this wind up the section 6.1. So next lecture we will solve some problems as suggested by you guys, that solve some complex problems. So I will try to solve some complex problem step by step to clarify the concept. And these are the some assignment problem for this section. So and you are also required to do some reading from the book. So please go through this section 6.1 and also the concept application of 6.2, 6.3 and sample problem 6.1, because we did the sample problem of 6.2 and the application concept application 6.1. So thank you very much, and next lecture we will solve some problem related to this section 6.1. Allah Hafiz.